Got it.
Uh, did it scream at you that the recording is in progress?
It's recording.
Okay. Recording in progress.
Recording in progress.
Welcome to the latest edition of Astroveo's Coast to Coast podcast of science, astronomy, and the world around us. My name is Joseph. My giggling counterpart is David, and we are just two friends who happen to be professional astronomers with a deep love of telescopes, astrophysics, and all things science. Today, we've got a great show for you. We're going to be talking about a very exciting new discovery of a neutron star at the heart of Supernova 1987A, the discovery of some new moons around Uranus and Neptune, and some of the amazing telescopes that make discoveries like this possible. And David's had a hand in building a lot of those. So you're going to be hearing from an expert today. I hope you guys appreciate how lucky you are. So why don't we dive into some of the new stuff? David, Supernova 1987A. I know I'm the supernova guy here, but that's got to be the most famous supernova of all time, basically, right?
Yeah, well, at least it's probably the most well known, or at least the most advertised. But there are plenty of other famous supernovae through history. There was the Tycho supernova of I
Crab
can't remember.
Nebula one.
Crab Nebula, probably 1042. So that's,
Yep.
We've known about that for 1,000 years.
And I'm personally studying 93J right now, so like I think that one's less known because it wasn't as obvious, but still super exciting.
It is very exciting. I actually remember that research coming out. I think I was 17 or 18, and it was like, holy cow, we've discovered this amazing supernova.
Oh my god, that
No,
don't need carbon dating to know how old David is.
I know that's right. I'm sort of giving my age away there slightly, but
we can neutrino date you.
yeah. Supernova date me, yeah.
Yeah, my body is 87A neutrino free.
That's
Thank
right.
you very much. I'm organic.
I suspect you've been hit by a great many other neutrinos. You're just fine.
Yeah. I'm GMO free, and GMO there is not genetically modified. It's giant Magellanic cloud.
Oh, that's lovely.
Oh,
Very
that
nice.
was a great one.
That's
I
pretty
will
cute.
laugh at my own jokes. Thank you. I know. I feel like that's kind of niche, but
Was
we
it?
keep talking about neutrinos. I feel like that's a little known fact, but when there's a supernova that goes off nearby, the whole Earth gets bombarded with a ton of neutrinos. Because even though they're super lowly interacting, they're like the main mechanism for they're one of the mechanisms by which the supernova explodes. The way heat is released is a big part of it is neutrino cooling. So if you see a bunch of neutrinos, which are usually the first to arrive at the same time as the light, it's a really, really good sign that there's like a galactic supernova going off or something similar like 87A.
Yeah, that's right. Absolutely. Well, I mean, I've done a little bit of study on supernovae, but you've been doing a lot of supernova research recently. So why do we care about whether stars go supernova or not? Why do we
So,
study?
that is a great question. A question I ask myself every day to convince myself that I don't just like watching things explode. uh, that's a really good question. Why do we care about supernova so much? I think that the energy for studying supernova has the same energy as people that would dig up corpses to try to understand better how the human anatomy worked, which like in order to understand hey, I'm gonna convince you, okay? In order to understand the stellar life cycle, right? And why do we want to understand the stellar life cycle? That's because stars make up almost everything we can see in the universe, basically. Like, although they're not everything in the universe, everything that we can see, almost all of it is basically starlight, in terms of like the brightest and most obvious stuff. And certainly everything you see when you look up at the night sky at night is starlight, or at the very most you're seeing light reflected from stars off of integrated flux nebula or surrounding gas. So stars super important, and understanding the way they die helps clear up a lot of questions about the end of their life, which in turn helps clear up a bunch more questions about their evolution as a whole. That's like why I think I personally am interested in supernovae, because there are different types of stars, and what type of star you have and its characteristics will inform how the star will explode. And so by better understanding the supernova themselves, we can get a hint into how stars are, how the underlying mechanisms that drive stars. But then there's also so you can get important information from supernovae as well. Like, for example, for type 1A supernovae, which I don't think 87A was. I think 87A was a core collapse.
That's right.
For type 1A supernovae, which are the collapse of the explosion of a white dwarf that's past something called the Chandrasekhar limit. Those explosions basically all look the same, and so they're a useful standard candle, which is helpful for areas like cosmology, where you want to measure distances in the universe. So there's lots and lots of interesting reasons to to look at supernova. But yeah, I mean, they're the corpses of stars, which we examine to understand better how the stars functioned when they were alive. Now, tell me that's not got some Leonardo da Vinci digging up graves energy.
Yeah, that's true. I think you're right. I think you're right, of course. But I think for me, certainly having been a spectroscopist for most of my career, the real beauty of supernovae for me is the fact that they disperse. They are basically the main mechanism through which anything that's not helium, hydrogen, and lithium, send that in a weird way, I suppose, hydrogen, helium, and lithium, are produced in the universe. Because as you know, the Big Bang only produced three elements. The
Well,
first,
hydrogen, helium, lithium, and deuterium
well,
as
deuterium isn't
well.
an element. Don't forget.
Oh yes, but it is a separate, distinct thing that's produced in the universe that does not require supernova to be produced.
That's true, but as I said, it's not an element.
It's
So
still hydrogen, but
yeah,
I
it's
think it's
okay.
important.
That's right. It's
I
fine.
had to say deuterium on my cosmology final, which means all you people listening have to suffer through it too.
Okay. Thank you for that. Thank you for that correction. But I refer to my earlier statement that only three elements were produced in the Big Bang. So everything else is nuclear processing inside stars that, of course, supernova and supernovae ejecta then disperse into the universe. And so every other, basically every star, every galaxy, every person, every planet contains the ejector of supernovae. And so for me personally, just that the mechanism to be able to produce all those different chemical species elements is just phenomenal. And of course, as you rightly said, it's the energy dumped into the local medium is phenomenal. It's just unbelievable. So they can stir up gas, they can influence stellar production inside even older galaxies. In fact, you can get starburst galaxies that can be triggered by supernovae. You can get spontaneous collapse of gas clouds to produce star clusters, all this stuff. So supernovae in and of themselves are just phenomenal.
I couldn't agree more. And there's the chemical element. I mean, that's like I can't believe I forgot that, but you're absolutely right. That's like the big thing is they fuse stuff together and then dump it into the surrounding environment, which is, I mean, what did Carl Sagan say? We're all stardust because
Yeah, yeah,
all the heavier elements in our body just came out from nearby
that's right.
supernovae.
Everything. Well, so the supernova, 87A was so cool because it was obviously down nearby satellite galaxy, the Large Magellanic Cloud. But of course, Hubble had just been launched. I think it was in '86. Had Hubble been launched at that point? Actually, Hubble was delayed by the Challenger disaster, so maybe it hadn't.
Hubble
Um,
was launched in 1990.
Oh, that's right. I kept thinking it was in '86, but it was supposed to go up on Challenger, and or one of those shuttles, and it was delayed. So that's right. We didn't have Hubble images till a wee bit later, but the fact that we could see the supernova, the ejector, the pressure ring explode and expand outward was just essentially one of the first times in human history we had sort of witnessed that and witnessed it with technology, which I think is another reason why it was just such a sort of cause célèbre for astronomers, is that we could see it happening in real time.
I mean, it's basically the most studied supernova ever because we got to
Oh,
see
by
it
far.
all the way from the early stages to the recent supernova that exploded in M101 23 IXF that like lit the whole astronomy world on fire, and that was at like 5 megaparsecs or something. And this is which was like, oh my god, closest supernova since the early 2010s, and like this was basically like next door. Like
It's
it
on the
was,
door. Yeah,
I
that's
mean, to have every area of physics basically was able to take advantage of this. Like you had particle physicists running all the stuff with the neutrino detections, and then you could probe the fluid mechanics and shock cooling via the expansion of the ring, and then you had all this stuff from spectroscopists and or spectroscopers. What do you guys call yourselves?
spectroscopists. You're right the
Okay.
first time.
Spectra men, spectra
Spectro,
people.
spectro people. Yeah.
Uh, yeah.
Well, it's funny you said that the next nearest one that we've studied recently really well is 5 megaparsecs. The one in the Large Magellanic Cloud is about 50 kiloparsecs away. So that's only
Wow,
1% of that
it's
distance.
100 times closer.
Yeah, exactly. So it's the fact that it's on our doorstep, as you rightly mentioned, meant also that we could study it. You measure it from year to year, and you see the ring of ejecta
Yeah.
expand, which means you get the energetics of the explosion because you can see the pressure ring expand outward, which is
Right.
just phenomenal. Just the shock front being able to move that quickly from year to year, or us for it to be able to see it. It's just unbelievable.
That's my specific area of research, and I think it's basically one of two where we were able to see that in real time, and the other one is the one I study. So
Yeah.
like it's you cannot oversell the ability to see a supernova expanding in those early phases and watching it, accumulate the circumstellar material around it, and then the ejecta slows down and becomes asymmetric. It's so unbelievably cool.
Yeah, I agree. It really is.
So at 50 kiloparsecs, it would have been visible to the naked eye, right?
Oh yeah, no, it was absolutely. Yeah, it
Yeah.
was absolutely. Yeah.
Okay.
I want to see what its peak brightness was. And I'm saying absolutely because I don't remember it that well. Yeah, that's right.
Don't you mean apparently, David?
Oh, very good. You're too good, Joseph. Too good. Its apparent magnitude peaked in 1987 May at a
Oh,
magnitude of about 3. So you're talking about like similar to some of the brightnesses of stars in the Pleiades, in the Seven Sisters.
that's unbelievable.
Yeah. Now, we wouldn't have been able to see it here from Boston. In fact, you probably would not be able to see it either from California, where you are,
But
because
most people would be able to see it even with a small telescope or some binoculars.
if no, it wasn't just the brightness. It's because it was so far south. It's in the southern
Yeah,
hemisphere,
yeah,
and
yeah.
it was minus 70 degrees. So if really, you'd have had to be in somewhere like southern Mexico and farther south to be able to see it.
Okay. I thought you were talking about brightnesses there, but yeah, and that's actually kind of a shame because it's spectacular to because I think there are people who are imaging, like even amateur astronomers now, who are imaging the nebula, right? The supernova remnant.
Oh yeah, absolutely.
You can't get incredible detail on it, but I believe that there are people who are imaging it.
In fact,
Uh,
Joseph, you
yeah.
know what? I'm
Uh-huh.
just realizing. Let me see if I can do this in real time for you.
What's that?
No, it's not quite there. So the image behind me is I look behind me, it's a green screen. Oh, what a dipstick. This is this 30 Doradus? Yeah, this is 30 Doradus in the
So that would be right next to 87A,
it
right?
is, that's right. I was actually just trying to line
Yeah.
it up. So there's the center of 30 Doradus. The supernova actually occurred down here, but it's the image the telescope I used to produce this image didn't have a big enough field of view. But had it had a big enough field of view, it would be about 2 or 3 of these image sizes to the bottom right corner.
Unreal.
Yeah.
Unreal.
I forgot about
Uh
that. It's in the Tarantula Nebula. Yeah, the 30
it would
Doradus.
have been just smaller than the field of view. That's a so close because that's a spectacular image, by the
I
way.
know, it was so close. In fact, you know what? I was probably deliberately trying to avoid it because it was so bright. When you take these beautiful, stellar images to make these color images that you and I produce, if you get any really bright star, it really can mess up the imaging. So.
Yep. And guys, David is an amazing astrophotographer. He's actually what inspired me to get into it. Even though I've been interested in astronomy and all this my whole life, like David's amazing images, and I got to see like behind the scenes of how he made them. I was like, I want to do that stuff.
Yeah, well, you're pretty seasoned at it now. There's some of the images you're making now are just beautiful. The Orion Nebula one I've seen you do, which we'll produce here on Astraveo at some point, is just stellar, quite literally.
Thanks, man. I appreciate it. And I can see you physically cringing every time I say, yeah, I didn't take any calibration frames today.
Oh,
I was
oh,
like, oh,
oh.
too soon, too soon,
Too soon, too
too soon.
soon. Oh. Well, I told you the story of the very first time I did imaging professionally. I had
Oh
two.
yes, that was the joke.
Oh God, it was just where I took no calibration frames whatsoever. Oh God.
The week of data down the
Oh
drain.
God, it was awful. It was so awful. God. I didn't
um,
know. I hadn't written down any color equations, so I didn't know what I had to calibrate out. Oh God.
I mean, back then all the equations were still in black and white, right? But
That was awful. Just awful. Black and white color equations. Oh my God.
uh, um, Sorry. But anyway, so the reason we're talking about 87A is basically when a star dies, it goes supernova and then kicks off this like huge, shock wave that collects all the dust around it and makes this beautiful, beautiful ring of emission that we can see. But the star doesn't always just get completely shredded. In some cases, like with 1A supernovae, the star will get sometimes completely destroyed. But for oftentimes in core collapse supernova like 87A, which it was, right? I keep
Yeah.
saying that, but yeah, it absolutely was. What am I saying? How could it not be? It had an ejecta. I don't know. Sorry. With 87A, I hope Andy's not watching this. I know. Andy's my supervisor. He's an amazing, amazing supervisor, but I don't want him to know how dumb I am. So with 87A, so most core collapse supernova, some of them leave behind a remnant. And so a really classic example of this is the Crab Nebula. It was one of the first, I think it was the first Messier object. Even though we could only see for a long time that it was just a nebula, just a big cloud of gas, once we got sufficient resolution, we found that in the exact center of it, there was a pulsar that we could measure, the period of and the rotation of. And so depending on how the star died and the specific characteristics, like whether it underwent thermonuclear collapse before it underwent gravitational collapse, it can determine the characteristics of the resulting star, of the resulting remnant. So sometimes that remnant can be a black hole, sometimes it's a pulsar or a neutron star. So it can vary, but the point is we expect a lot of these supernovae to leave remnants behind, and we've been trying to detect the remnant in 87A for a long time. And very, very recently, like as of this week, the JWST, astronomers using the JWST spotted signs of a neutron star in the center of the explosion. And basically, we didn't detect it before because there's so much thick gas and dust around it that you can't really observe it directly. But as the light from the neutron star passes through that dust, it leaves a very characteristic signature in the spectra. And so it was a spectroscopic discovery, actually, pretty much, that showed that the gas around the remnant was being ionized in a way that was consistent with the radiation characteristics of a neutron star. And this is one of those things that we suspected for a while, because we got a huge blast of neutrinos from 87A, but so we were looking for a neutron star, but we didn't. We hadn't found it for a long time, but now we finally have, and that's incredibly exciting. So hats off to the supernova team that discovered it.
Absolutely. Woo! Oh, you did that. That was nice. That was nice. Well, I think it's one of those things as well, even if you could observe it directly at 50 kiloparsecs, neutron stars, obviously, as we know, are very, very tiny. Surface areas are just incredibly small, possibly, 10, 20, 30 kilometers across. So the magnitude of a neutron star at 50,000 parsecs would be extremely low, and even JWST wouldn't be able to observe it. So I don't think we can image it directly, but we can see the indirect effects of it ionizing gas around it.
Yeah. And honestly, a lot of discoveries in astrophysics are that kind of indirect stuff, because it's just things are too small and too far away. The only thing we got is the light.
Yeah, well, I mean, look at black holes, for instance. So effectively you can't see them, at least not directly. Even the black hole imaging we do, you don't see the direct black hole, but you can see things. For instance, that you see X-rays being produced around the event horizon, where you get pair production, positron electron production right at the event horizon. You see orbits of stars orbiting the black hole at the center of our galaxy. You see these sort of hypervelocity stars, and when you work out the mechanics, it's like, oh, there's 1 million solar masses there. Like, well, you've got 1 million solar masses and it's producing all this energy, but you can't see it. What else can it be?
Right. Clearly a dark matter clump.
There you go. Yeah.
Actually, I had a really interesting experience the other day. I was taking Pickles for a walk, and he just got very excited hearing me say that. Sorry, buddy. False alarm. False alarm. I know, the poor guy. And I was taking it for a walk, and I smelled smoke. and it was from some. I'm not sure exactly what they were doing. I think it was like some exterminator like killing a wasp nest or something, but they were like using fire. I don't know exactly know what they were doing, to be honest. But I identified them with my eyes pretty easily. But I thought about it for a second, and I was like, imagine if I was blindfolded and had noise canceling headphones on, and all I could smell was the smoke, and that was all the info I had. Could I locate the guy? And that was seemed like an impossible problem. And then add, more complicating factors like there's a background of smoke, and the wind's blowing the smoke every which direction, and there's stuff in the way of the smoke that causes the smoke to go around and change its original path, and it's like, well, that's astronomy. Like, and
imagine if you were able to take spectroscopy of that smoke and realize it was the same chemical composition of the smoke used to do whatever that fellow was doing.
Right.
That's what we do.
But I think that's why I feel like Spectre is like an OP, like, it's a really overpowered knowledge that we have access to. It's so informative.
Oh, it's amazing.
Yeah. It goes from just being the blind deaf guy, sniffing the smoke, to the science. I think not that photometry based stuff isn't science. Actually, my research is primarily photometry based, but it is like truly astonishing the volume of information that you can get from the spectra, and this kind of discovery is just more proof of that.
Yeah, thoroughly. Well, I mean, it's like many things in life. You need more than one feather to your bow to be able to find out the real truth of something.
Yeah, a feather to your bow. That's a very common thing people say.
Yes. Well,
sorry, for people like me, what does that mean? I'm asking for pickles.
Oh, maybe I conflated two different expressions there. String, multiple strings to your bow.
Okay. Oh, you meant feather in your cap, maybe?
Maybe I was getting confused with that too. But what I'm trying to say is you need multiple avenues of investigation to find out the actual truth.
It's okay. As the great Avi Loeb once said, I'm not the brightest. What did he say? The sharpest cookie in the cookie jar, I think was the expression.
Yeah. Well, given that he advocates lumps of rock in space being alien spacecraft, I think we can take that.
I'm not the brightest bulb short of a six-pack.
No. Anyway, that's what I meant to imply. Sorry, I did conflate my colloquialisms there. I do apologize. Yeah, no, one thing I love about spectroscopy is that you can work out an awful lot of things which are independent of distance. And with photometry, often distance is sort of thrown in there as a really complicated factor, which you can't easily work out. And so I love the beauty of spectroscopy. It's very clean. It's very the results are the results. There's very few alternative explanations.
Not with that attitude. The LCO just went through a nightmare very recently because we realized that we realized that we had a sensitivity dip. We had a dip in our sensitivity function for the Floyd spectrometer right around the hydrogen beta line, which if so like what was happening was if the source was redshifted by just the right amount, the hydrogen beta line would fall right into the sensitivity dip, and we'd like be off by a bit, and so it was causing some problems. We did figure it out. That was very confusing to untangle.
That's a pain in the derriere.
So that's for the JWST stuff, but there's also some more exciting news. We've spotted. I mean, I feel like people like to think that we've learned everything we possibly can about our solar system, but that's definitely not true. And we actually just found new moons around Uranus and Neptune, which is pretty cool. So, like,
how were they found? Do you know with which instrument?
So it was a Carnegie astronomer. The instrument was it was made
Scott Shepherd.
It was Scott Shepherd. How did you know that?
Yeah, I know Scott Shepherd. Yeah, I've done some work with him. He's a really amazing moon and asteroid guy.
What a legend! Look at this guy. It's like, oh my god, oh my god, you're a freaking legend, man. So did you work with Scott Shepherd like on anything or?
Yeah, I've done some observing with him a wee while ago, but I did some rotation period work of asteroids, the Trojans around Jupiter. But Scott's I can't remember, he works often with a companion. I can't remember his name now. But Scott does some amazing work in solar system dynamics, discovery of new objects, moons, that kind of thing.
Yeah. That's super cool. It's so cool that you like, oh man. you know, I get pretty excited when I get to tell people that I know you. So I can kind of like
Who?
that's my biggest claim to fame. I know David James,
That's a pretty small claim right there.
not the Olympic athlete. Uh,
There's
but so
actually,
yes, sir.
sorry, there's a goalkeeper in football in British soccer who used to play, who's called David James. Well, he still is called David James.
What there's an Olympic athlete named Michael Johnson who is my old supervisor for those that don't know at
Yeah, right.
Harvard. And when I first joined his group, before I met him, I did a Google search and was very confused for a while.
Given that
I
he
was
was the
like,
fastest man on Earth for 10 years.
yeah, I was like, and then he switched to physics.
I know.
I
Well,
was like,
he
whoa.
was just as fast as an electron. That guy. Holy cow!
I was like, yeah, Olympic athlete and star physicist. His parents
Yeah,
must be
that's right.
very proud.
He had a
um,
beautiful upright running style. He used to be so rigid from the hips up, but he was so fast. Oh, I loved watching
are we talking about the same Michael Johnson here? Because uh, I my height terminates at our Michael Johnson's like midriff. So I mean, I have no information about the rigidity of his upper body.
Yeah, he's about my height. He's about 6'3", 6'4". He's a big
He's
boy.
which Michael Johnson?
The astronomer.
I think he's taller actually.
Yeah, he might be an inch or two
I
taller
think
than
he's
me.
like sick. He might be sick. Like I mean, he was.
He
I
might
used
be
to say like
6'5",
I
6'6".
just for the record, if Michael ever sees this, I loved being Michael's student, and I hope to again someday. But I used to joke that the toughest part about being Michael's student was that you're always looking up to him.
Oh, very nice.
In both ways.
Yeah.
But anyway, to answer your
Yeah.
question though, so the discovery was made using observatories in Hawaii and Chile. I'm not sure which ones they were, but the follow-up observations were done with the Magellan telescopes, which I think
Uh,
are in Hawaii.
so no, so Magellan is in Chile. It's
Oh, it's in Chile.
the Barde and the Clay telescopes, 6.5 meters.
Okay.
Yeah, so that's why you need them, because of course these are super faint. So he was probably doing dynamical imaging, as in watching them, move. So I
Okay.
suspect he may
Oh,
have been.
actually, no. So I did some research into the method. It wasn't dynamical imaging because I was curious about that. Like I was like, I'm always interested in stuff because it's like adaptive like speckle optics or anything. So what they did was they did this technique where, and I don't understand this actually, so maybe you can help me out. But the way they say the technique works is they move the camera at the same rate as the planetary system. So all the
Yeah,
stars and stuff appear fixed, but the the planet and its moons don't. But I actually didn't understand. Sorry, all the stars and stuff appear like trails, but the
yes.
moons and stuff don't. And I actually
That's-
included a picture of this on the blog.
Yep.
And by the way, the blog has now passed 11,000 views thanks to our amazing viewers. So keep following us
Congratulations.
for a preview on the stories that we'll be talking
Yeah,
about.
that's right. So this is sort of inverse dynamical imaging. So normally with dynamical imaging, what you do is you take a series of photos or images with the telescope, and then you look for things that move. That would be something like a planet or meteors or asteroids. In this case, what they've done is they've done non-sidereal tracking, which means they're not following the rotation rate of the Earth. They're following the rotation rate of Uranus or Venus, which Uranus this is. So this is Uranus right here, not the yellow arrow. The yellow arrow is pointing to the moon. The bright object is Uranus. And
Not
all
this thing on the left.
Oh, yes, you're quite right. Sorry, thank you. Yep, you're
Yeah.
quite right. That's it on the left. And then you're seeing these streaks because, of course, Uranus is moving against the background of stars because it's a solar system object. But if you set the tracking rate of the telescope to Uranus, anything that moves with Uranus, as long as it's not the moons aren't orbiting really quickly, like the Galilean moons, for instance, will not be streaked because they are co-moving with the planet.
So that's actually what I was wondering. I feel like the is maybe why are the orbits so slow? I guess is what I'm wondering. Like, I
Well,
guess. Oh, I see. Maybe this is because this technique only works on. It's like self-selecting for slow orbits because both of these orbits are slow. One of them is a 27
yeah,
year orbit,
27. There you
and
go.
one of
That's right.
the other one on Uranus is 680 days.
Yeah.
Okay.
Yes, that's right. So the orbital period is so slow that even in, say, a 1 hour exposure, they don't appear to move, especially relative to the background stars.
Okay.
In fact, yeah, I mentioned that Scott often works with a colleague. Here it is. It's Chad Trujillo. Yeah, that's right. And
Yep.
so, yeah, this is inverse dynamical imaging. And so the reason why the dot at the end of the yellow arrow, which is one of the new moons, appears to be static, is because it's co-moving with the Uranian system as it orbits the sun. Even though, of course, it itself is moving, if it's a very long period object, like has a period of years, in a 1 hour exposure, it doesn't appear to move.
Okay, that's unbelievably cool.
Yeah, it's
Uh,
amazing. Yeah.
and it was, I mean, this moon is just 5 miles wide.
Wow, that's amazing.
Like, it's kind of unreal to think that like you're able to see an object 5 miles wide at the distance of Uranus.
Yeah, absolutely. Well, given that Uranus is obviously physically very big, much bigger than the Earth, it begs the question whether it's a real co-produced moon or whether it's a captured meteor.
Because you're getting more Kuiper belt objects out there at that distance. So not too many at Uranus distance, but like you're gonna have some free floating rocks.
Oh yeah,
Uh,
absolutely. I mean,
so
if it's 5 miles across, 8 kilometers across, it's essentially a pebble.
yeah, it literally is.
I
Yeah,
mean, seriously, it really is compared to the size of Uranus itself. I mean, even
that could
compared to the
that could potentially, if you're right and it's a captured object, that could be a next, like, because the Ultima Thule mission, although they renamed it, but I don't remember what the new name is, Arakoth or something. I forget what it is, but the New Horizons mission, when they went to Ultima Thule, that helped answer a lot of questions about the pebble accretion process and the formation of the solar system, because Ultima Thule was so old and so well preserved. If this is a captured moon, which I bet it is, with given how small it is and how far away it is from Uranus, if it is a captured moon, this could be a much easier target than trying to pin something in the Kuiper belt down, because we know the period now. We have pretty much exact astrometric coordinates as soon as it's observed, and with the follow-up observations. So that could be a really interesting target for a future mission.
Yeah, that's right. That's right. Yeah. Although, I suppose so. It depends what you'd want to find out about it. Because I mean, what just because it's captured, perhaps the real interesting thing would be its chemical composition, whether it had processed or reprocessed material on the surface.
Well, and not just the chemical composition, but like, for example, with Ultima Thule, it had quite an unusual shape because it was basically two pebbles stuck together.
Yeah, that's right.
And that was a big, validator for the pebble accretion hypothesis. And
Mhm.
then there wasn't just the chemical composition. The fact that it was tumbling was, I think, an important indicator of something. That was really interesting. And even just the chemical composition, having access to the chemical composition of an object that may have been effectively untouched since the beginning of the solar system is it's like a time machine, basically.
That's true. I mean, pristine material. There's probably millions of those types of object, even in the asteroid belt. So I
Oh,
don't think.
I mean, I think literally probably. Well, I don't know what the estimate was for like Kuiper belt objects, but the problem is with the asteroid belt, it's hard to distinguish the new material from
That's right.
old material. Yeah.
That's right.
Uh, but I love this kind of stuff though, because it really, like, there's so much we don't know about our own solar system yet, and
I know.
stuff like this.
True.
And this technique is incredibly cool too. I remember you'd be surprised, you could see Uranus with not too big of a telescope, but I still remember the first time I saw Uranus through the 6 inch. Oh my God. That was like a momentous first view. Like, it felt to me almost like seeing the Galilean moons for the first time. I think it was less life changing because seeing the Galilean moons for the first time was one of the things that set me on like the astronomer path.
Yeah.
But like, it felt as crazy, like, because I felt like coming into that, looking at Uranus, knowing how far away it was, knowing the math, knowing the size, and you can tell, it's not a star.
Yes.
You can tell it doesn't look like it. That was it was just one of the most. I'll never forget that moment. The first time I saw Uranus through a telescope was unbelievable.
Yeah, I couldn't agree more. I've always liked Uranus. I think we did this when we did our favorite planets on one of the earlier coast to
Yeah.
coast. Is that I just love the fact that it's got a very faint ring system. It's still got this beautiful deep blue sort of greenish hue because it's all the methane is absorbing the infrared. the redder light, sorry, and the fact it's tilted on its side, it looks as though it's been hit like a bowling ball hitting skittles.
It's such a weirdo.
I know it's amazing actually.
I
Yeah.
it's a great planet. It's easily top 10 planet in the solar system.
Oh, easily.
Easily.
Well, probably down to top 9 now, maybe top 8.
Yeah. Exactly. It's one of the top 50 major planets in the solar system.
Of all the planets we know in the solar system, it's one of our favorites.
Of all the planets I've ever seen, Uranus is one of them.
Amazing. Well, this wraps up another presentation for Astraveo, where we go from geek to chic by sharing our passion and excitement for all things scientific, especially astronomy and in the mysteries of the universe. If you enjoyed this video, please hit the like button, and in the comments below, please leave us your suggestions for future presentations. We'll get right on it. And don't forget, you can join us on our journey by subscribing and hitting that bell. He's Joseph, and I'm David, and together we're Astraveo. Thanks for watching.